So let's conclude this chapter with what happens in the other oceans. So we always look at El Niño as the poster child for explaining ocean-atmosphere interactions, mode of climate variability, how climate variability affects global teleconnections, and so on. So if you look at this map, you see the curious changes in the tropical circulation as well, right? During normal times you have deep convection here and you have sinking over here. This is the Pacific Walker Cell. You have sinking in over Western India, Eastern Africa, Western Indian Ocean, Eastern Africa, which is the Indian side of the Walker Cell, and of course you have another convection center over the Amazon, and West Africa has a desert, West Africa has a monsoon as well. But the main thing you would notice is that the zonal extent of the tropical Pacific is far, far, far greater than the zonal extent of the Indian and Atlantic Oceans. And we've talked about how the mean sea surface temperatures and rainfall distributions are dramatically different over the Indian Ocean because of the monsoonal circulation, which is northeasterly during the winter months, southwesterly during the summer months, and intermonsoons are rather weak, and so on. And the trade winds are mostly confined to the south of 10 south and so on. And there is no strong upwelling here. This is in climatological condition the Indo-Pacific warm pool, and colder temperatures happen here, especially during the summer, boreal summer. The Somali upwelling associated with the southwesterly monsoon is very strong, and you get some of the coldest upwelled waters here. Okay, so we also talked about how the convection shift and so on drive waves in here, Kelvin waves and Rossby waves, and how Kelvin waves travel much faster than the Rossby waves, and how they are playing a part in terminating the Birkenes feedback, as well as initiating often El Niños with Kelvin wave pushing the thermocline down, warming the sea surface temperatures, and changing the SST gradient and the winds to reinforce the feedback and so on. So if we look at the Indian and Atlantic Oceans, would there also be El Niño like zonal modes of variability, east-west modes of variability in those oceans? Well, it turns out that there are, and the oops, am I in the wrong direction here? Okay. So there is something called the Indian Ocean Dipole, and there has been tremendous debate about whether it's really a dipole or it's a monopole, and whether it's really independent of El Niño, and whether it really does anything in terms of teleconnections and so on and so forth. But let's not get into those kinds of details and look at what is the most interesting scientifically robust knowledge we have about it, and that is that if we look at the Pacific, which unfortunately I have to, so if you look at the Pacific, we said there is an Indo-Pacific warm pool, and there is a cold tongue here, and the Western Indian Ocean is colder. So you have rising air here and sinking air here and here. So you can think of this as almost a continuous system, which is often referred to as the Indo-Pacific tripole. And you can see that somewhat here, that when there are coldest temperatures, anomalously cold temperatures here, those cold temperatures are connected all the way into the east here, and remember this is cooler than normal during an El Niño as well. So obviously that means that the convection perturbation here also affects the temperatures here, and of course this part of the Walker cell is also affected. But nonetheless, there are years when this east-west contrast gets very strong. Remember that normally these are warm temperatures. When they get anomalously cold, there is anomalous warming on this side, so associated convection perturbations, and you have a similar perturbation to the local Walker cell here, where instead of the subsidence here and rising motion here, you have a reversed Walker cell locally. So you have anomalous rain here, anomalously dry conditions here, here. So without worrying about exactly how this is forced and whether this is related to El Nino, you can see that the Indian Ocean has an El Nino-like variability, which is the zonal mode of variability. And there are many studies that have shown that there are also waves involved here, but the situation here is different because the waves go into the Bay of Bengal and come back and go down here into the Indonesian seas and around down Australia and so on, and the same on this other side. So there is something like a Bjerknes feedback that happens here as well. The biggest thing to explain is when does this peak. So this peaks in September, October, November. So it doesn't last for as long as an El Nino lasts, which we said typically 9 to 12 to 18 months. So this happens on 3-month time scales, and there have been arguments made that it affects the monsoon, but remembering again that the monsoon happens in June, July, August, and El Nino is a monster which can affect the Indian monsoon. It isn't clear how this is related to El Nino and whether it's the monsoon that is feeding back to the Indian Ocean dipole, or whether the Indian Ocean dipole that peaks in September, October, November can really influence. That is a much stronger heat source that happens during June, July, August, and so on. So most conclusions seem to tend towards saying that this is basically like a tail of an El Nino. So it is part of the Indo-Pacific tripole, which means you have a center here and center in the East Pacific and a center here. Nonetheless, it is important to know that this happens, and its periodicity is very episodic. Then there are debates about whether they are occurring more frequently during global warming or whether it's natural variability in terms of decades where there are fewer Indian Ocean dipoles than other decades, because there are also decades where El Nino seems more active than in other decades, which is approximately visible in this time series we saw here. So if you look at this longer time series, can you convince yourself that maybe there were more El Ninos here than here? Wow, that's a longer debate. So there is something called ENSO variability, means number of ENSO events that happen in clusters of decades. So there is a similar argument about whether Indian Ocean dipole is also happening more frequently in some decades than in others. Okay, so it is definitely a zonal mode of variability, definitely has some Bjerknes feedback when this gets very strong, so that even if El Nino triggered it, then maybe something locally happens here that is related to east-west sea-surface temperature gradients, winds, and associated feedbacks like we saw in the Indian Ocean. Of course, there is a similar thing in the Atlantic as well, and again, Atlantic is a very small basin, so Kelvin waves, which would take 3 months to cross the basin in the Pacific, cross here in about 10 days, similar to the Indian Ocean, and Rossby waves take 1 month instead of 3 months or 12 months based on where they start. And so the east-west contrasts are quickly removed by the waves going back and forth. The Atlantic has an additional complexity that the intertropical convergence zone, or the ITCZ, is very close to the equator, so when it goes north-south, even on a seasonal basis, it can touch the equator and set off Kelvin waves and so on. And the Atlantic Niño also happens very episodically, and there seems to be more robust evidence that an Atlantic Niño affects the Indian monsoon. So then the question arises again whether this is independent of the El Nino. People argue that it is, and whether that is closely coupled to the variability of the ITCZ, which also has been argued that they are the same thing. And of course you also have to worry about whether the Atlantic Niño can add to the El Niño's influence on some of the teleconnections we looked at, or whether it subtracts from it, and so on and so forth. So you can see the precipitation anomalies during June to August. So this peaks during June, July, August, again only 3 months. So the idea of why El Nino peaks where it does, why the Indian Ocean dipole and Atlantic Nino peak where they do, is still not completely resolved. The June, July, August monsoon is explained more easily because of the sun moving, heating the land, creating the land-ocean thermal contrast, and so on. But these zonal modes are phase locked, so they occur at a certain time of the year, and those are explained mostly in terms of how they happen rather than why they happen. So there is some fundamental understanding that still is not complete in many ways. Nonetheless, the main question comes down to two things: whether they can be predicted so that their teleconnections can be predicted on land, so that you can see whether a drought is coming, flood is coming, and so on. But also how they are all responding to the global warming. And you can see that in some sense, when there is such a large ITCZ that runs across all the tropical basins, then whether the ITCZ movement itself is somehow fundamentally linked to these zonal modes of variability. So those are very deep, difficult questions which is beyond this introductory course, of course. Finally, there is another interesting mode called the Arctic Oscillation, also known as the Northern Annular Mode, similar to the Southern Annular Mode, keeping in mind that the Southern Annular Mode has an ocean that is continuous like a channel, whereas in the north we have land that is quite extensive around the Arctic. Okay, so monthly time series here from 1979 to 2018 with the 10-year smoothing and sea level pressure anomaly correlations in here. SLP anomaly correlation maps have contour intervals of 0.1, and the contour colors separate the correlation coefficients of plus minus 0.66, which correspond to high-low pressure systems, which means the waves in the annular mode. Climate indices obtained from NOAA and reanalysis, and so on and so forth. So this is the Arctic Oscillation here, which is defined in a certain way with some index. North Atlantic Oscillation we already looked at, and I already mentioned that Arctic Oscillation and North Atlantic Oscillation are closely related. And this is our Antarctic Oscillation, or the Southern Annular Mode. And you can see maybe there is an out of phase relation, but it's not that obvious. There are times when they're out of phase, but here you can see that these are somewhat in phase and out of phase here. But this relation is fairly close. You can also see the sea level patterns as correlations. So you have high pressure here with low pressure around. This is why you would call it an annular mode, whereas the annular mode is slightly broken up during the North Atlantic Oscillation. So it's possible that North Atlantic Oscillation is a variance on the annular mode, where the annular mode pattern is broken up by the North Atlantic interaction of the Azores high and the Icelandic low. And Antarctic correlations you also show the annular mode pattern. So here you have Australia, South America, and Africa. So you can see which section is which. So again, high pressure in the middle and low pressure kind of pattern around. Of course, this depends on which phase you are here in here. It obviously is the opposite phase when you are in the other phase of NAO, AO, and AAO. Okay, so these are also very critical, and they have an impact on the temperatures, precipitation or snowfall rates, and sea ice extents, and so on over the polar regions. So that's another fundamental mode of variability. I think this is the last slide where there is another process. Oops, I think maybe I skipped the wind SST evaporation feedback, unfortunately, somewhere. Yeah, so that's, sorry about that. No harm done. So just remembering the climatological winds and that we are talking about anomalous winds, typically there is another process that's very fundamental called the wind evaporation SST feedback, which is a positive feedback in the tropics that is capable of amplifying an anomalous meridional SST gradient. So let's say there are prevailing easterlies which are the normal. So if you going in a positive feedback loop, you can start anywhere. So let's say you have a meridional gradient in here with warmer SSTs and colder SSTs. So you have low sea level pressure and high sea level pressure, which should drive a wind anomaly, and then you add wind anomaly related to the pressure gradient. But because of Coriolis, you create westerly anomalies here and easterly anomalies here. So this adds to the prevailing easterlies and increases the wind speed, latent heat loss, and colder SSTs, whereas here it weakens the easterlies and reduces the latent heat loss. Remember, latent heat loss is related to wind speed, so that enhances the warming. So you get less latent heat flux, more latent heat flux, reinforced warm cold SST pattern, and the SST gradient. So this is argued to be important in many of the modes of variability at not only interannual timescales but also at intra-seasonal timescales. So another process that is invoked for low frequency variability is called the Re-Emergence Mechanism, where during one season you may have certain amount of surface cooling, turbulent kinetic energy, and so on, which creates deep mixed layer, and there is a low exchange of energy with the deeper ocean. So this is going deep and this is going in time. And here, let's say warm season comes and heating creates stratification and the mixed layer shallows. So this cold water that was created in the cold season is sitting here, and when the next cooling season comes, depending on the turbulent kinetic energy and interannual variability and so on, the previous year's cold waters can get re-entrained into the mixed layer during the cooling season. And of course this can happen at various time scales, where one year which is more cold or less cold may leave less cold water or more cold water, which can then affect the following year's cold season. So you are automatically creating a interannual variability here that is purely related to how deep the mixed layer was in one year. So this is the kind of re-emergence mechanism, and it is confirmed in some parts of the North Pacific, and it is argued that it's not occurring in some other places like the eastern part, where there is another mode of variability called the North Pacific gyre mode, or North Pacific gyre oscillation, and so on and so forth. So we often find statistical patterns that have certain time scales, and then we try to understand the processes behind them. And the key question is always to see whether they are real modes of variability or they are just artifacts of leftover residuals from other modes of variability like El Nino and La Nina, which are producing low frequency rectifications. Okay, so let's leave this chapter here and come back and look at response of the atmosphere and ocean system to buoyancy forcing, or ocean response to buoyancy forcing. Okay.